Okay, thank you for coming, everyone. My name, as you can see, is Peter Diggle, and I'm a professor in the Faculty of Health and Medicine here at Lancaster. And one of my major research interests is in using statistics and statistical thinking, statistical models, statistical methods to understand the geographical variation or the spatial variation in disease outcomes. And that's what I want to talk to you about today. To sort of set the scene historically, we can go back to the mid-19th century in central London. This is Soho, which some of you will know for reasons other than public health. And at the time, around about the mid-19th century, there was a major cholera epidemic in this part of London. And the prevailing wisdom back in the 19th century was that cholera was spread through contaminated air that people breathed. The physician John Snow was sceptical of this explanation, and he took what was at the time a radical step of mapping the locations of the deaths, the cholera deaths, in this part of London. And with the benefit of hindsight, once Dr. Snow produced his map, you can see very clearly that the concentration of deaths is in the centre of this map, and in particular, it's concentrated around a water pump, infamously known now as the Broad Street pump, which turned out to be the source of contaminated water that explained the epidemic very well. So that it was then accepted, after some controversy, that this was a waterborne disease, not an airborne disease. And it's the first example of using spatial or geographical mapping methods to understand the distribution of, and therefore the factors causing disease of various kinds. Now, moving forward to a contemporary map, this records cattle holding farms in England and Wales around about the turn of the century, and it's the results of a programme of testing the cattle herds for bovine tuberculosis. And the colour distinction here is that the red farms have tested positive and the blue farms have tested negative. And again, there are some very obvious patterns that show up on that map, and in particular we need both colours here because, unlike Soho in the 19th century, it's not the case that farms are equally spread all over England and Wales. So that there are a lot of cases in West Wales, there are also an awful lot of farms. This actually is a more worrying phenomenon because proportionately there are many more red cases than blue cases in that area. And to kind of refine that qualitative judgment, we can build a statistical model that quantifies the risk in probabilistic terms of a farm being located at a particular place testing positive for BTB. And the result of that exercise gives you this smoothed out picture here, which actually confirms that the most serious problem is in the Midlands rather than in the far West Wales region. Now here, you can see another dimension coming into the problem. We here have time as well as space. This is the foot and mouth epidemic, which devastated the farming industry in Cumbria, not far from Lancaster, in 2001. And the spatial pattern here again is very obvious. The epidemic was largely, but not completely, concentrated in the northern part of the county. And as you saw from the animation, there's also a very important temporal dimension. This is an infectious disease which is incidentally spread on the air rather than through water. And once a farm is infected, its near neighbours are likely to become infected soon after. And it's important to understand that as a model because that affects the policy that the government instituted at the time of ring culling. In other words, once a farm is infected, susceptible farms in the neighbourhood would have their stock slaughtered. And the key thing here is that we're dealing with phenomena which have obvious qualitative features, but to be precise about their properties involves uncertainties of various kinds. Uncertainty in the data, because we can't be sure that we've got complete information in the data. Uncertainty in the process, because the process whereby some people or farms catch a disease and others don't is inherently stochastic, meaning it involves a random element and we can't predict with any certainty which farms are going to succumb to the epidemic. And also uncertainty of a deeper kind, which is that we don't necessarily understand the underlying process. So that takes us through, quite naturally, to the idea of statistical models, because the essence of statistics is dealing with uncertainty. It's dealing with variation that's not completely predictable by well-known, well-understood mechanisms. So when a statistician talks about a model, they're not talking about a scientific truth, like Newton's laws of motion. They're talking about a device that they use to answer questions by marrying data with science. And the key statistical element is the notion of acknowledging and quantifying the degree of uncertainty in both the model and in the conclusions that you are legitimately able to draw from the model. And so it's important that those models respect the underlying science, but equally in many branches of science that underlying knowledge is imperfect. And so we have to tread a line between analysing data and actually analysing scientific theories, and hopefully marrying the two. And that's why statisticians are reluctant to make their models too complicated, because they know that it's an impossible goal to have a perfect model. And so they tend to be arguing that models should be kept as simple as possible, provided they're consistent with the available data. And I've already acknowledged that they should also make sense to the scientists who originally collected the data in the first place. An analogy which I'm rather fond of is with the great composer Mozart, who, rumour has it, presented one of his new pieces to his sponsor, the Emperor Joseph II, who was a pianist of somewhat limited ability, and the Emperor Joseph's response was that there were too many notes, Mr. Mozart, too many notes. To which Mozart was rumoured to have replied, only as many as there needed to be. So in a statistical model, there is only as much complexity as there needs to be. And that's the difference actually between statistics and mathematics. Mathematics has no penalty for complexity. Statistics penalises complexity, and you have to keep your models simple whilst actually answering the question. I'm going to skip this example in the interest of limited time and move on to my main theme, which is the problem of river blindness in equatorial Africa. This photograph is very poignant, and if you scour the web or your local library, you'll find many similar photographs, because river blindness is a condition that for many years devastated poor rural communities in the wet tropics, turning substantial proportions of young to middle-aged people blind, and that has obviously major repercussions for the health and welfare of their families and their communities. Where does river blindness come from? Well, it starts with you being unfortunately bitten by this little creature on the left, and if this fly is infected with a particular form of parasite, that parasite will be transmitted into your bloodstream, and if left untreated, it will eventually, not with probability 1, remember, we're dealing with uncertainty, but it puts you at risk of eventually going blind, suffering from onchocerciasis, commonly known as river blindness because it's associated with wet and hot conditions. Wet because that promotes the breeding sites for the fly. Okay? Now, I did say that this is what happens if you don't get treated, because there's a very effective prophylactic treatment for onchocerciasis. It's called Mectizan. It's a drug which is available at relatively low cost, and indeed for the last 15 years or so, a pharmaceutical company has been donating supplies of this drug free of charge to be distributed prophylactically to complete communities in the affected parts of Africa. 60 million or more treatments to date. And that has a very good track record both of being an effective prophylactic, if you take one pill a year, but also being a very safe drug. Unfortunately, after a few years, a problem emerged. And the nature of the problem was this. A previously very safe drug was observed to be producing severe reactions, occasionally fatal, 100 or 200 fatalities to date, I believe, that order of magnitude, in people who were heavily co-infected with a second parasite, lower lower. This is a lower lower parasite. Lower lower causes a disease colloquially known as eyeworm, which is unpleasant but not fatal and not blinding and not generally considered very serious. But for reasons which at the time were causing a puzzle, but have since been investigated by a lot of very clever biological science research, if you're heavily co-infected with the river blindness parasites and the lower lower parasites, you're at risk of an adverse reaction. So the WHO, who are monitoring this program, said we need to know where the high-risk areas are for lower lower. How do we find them? Well, you need some data and you need a model. So what I'm showing you here is a schematic of the kind of data that were collected. You have to imagine that you're walking from west to east along a transect in the affected part of Africa, somewhere near the equator, and as you walk along you occasionally come to a village community, and in some of those village communities you decide to round up some volunteers and take blood from them. And then you can look at the blood under the microscope and you can look at the proportion or prevalence of people who show evidence of lower parasites in their blood. And that gives you an estimate, or more honestly a guess, as to how serious the lower problem is in that village. And off you go, and as you go along west to east, you notice two things. One is you notice that it's getting hotter and it's getting wetter. And the other you notice is that when you do stop and take an observation, you're tending to get higher values. Right? So we know that that makes sense because we know the breeding habits of the fly that spreads the disease. So what we do is we try to build a simple model which represents how that change in the environment, the temperature and the wetness, affects the prevalence. And you can fit a nice simple curve to describe roughly that relationship. And superficially, that curve is consistent with the data. So it meets my requirement of a statistical model, and it's consistent with science, namely that it goes up when it's hot and it goes up when it's wet. The other nice thing about it is that because I can get data on temperature and vegetation by remote satellite technologies, I can actually predict the value of this curve anywhere, even if I don't have any surveys of villages. I can record the temperature and the greenness, and I can predict the lower prevalence. The problem is that if you go beyond standard routine statistics, you find that this model is not consistent with the data. And in order to make it consistent with the data, you have to draw a rather more wiggly curve, indicated there by the red dashed line. Now, any fool can draw a wiggly curve through a set of data, but it takes a statistician to draw the right wiggly curve. And the reason is that we're getting these black dots by taking, let's say, 100 people, and suppose we find that 20 of them test positive for lower. Well, we can then work out, using simple probability theory, that that doesn't really mean a prevalence of 20%. It means that the prevalence might easily be anywhere between 10 and 30%. But it couldn't be 1%, and it couldn't be 50%. So we know how close those black dots should be to the model. And the wiggly curve is just the wiggly curve that makes the errors of the size that they ought to be. Remember Mozart? Only as many as there needed to be. Okay? Furthermore, we invoke, and the data support it, what's sometimes called the first law of geography, which is that all things are related, but close things are more strongly related than distant things. And in statistical terms, that means that if this village is below average, neighbouring villages are probably below average. Okay? And so that's again why the red curve deviates not arbitrarily, but smoothly from the blue curve. And so that red curve is now our statistical model, which it respects the science, it respects the data, it incorporates the first law of geography. And using that model, we can produce this map. And this map is a rather rich representation of the lower phenomenon throughout Cameroon and small parts of Nigeria, and it bears quite close inspection because it contains a lot of information. Why 20%? Because the WHO have decided, after much expert discussion and debate, that if a village was known to have 20% or more lower prevalence, the prophylactic medication would not be rolled out without first putting in precautionary measures, essentially to have medical help on hand for the people who suffer the severe reaction. So their policy intervention threshold is 20% prevalence of lower. But there's an awful lot of areas on this map where there isn't any survey data, and also there's some areas where the blacks and the blues are intermingled in what seems like a rather unsatisfactorily random manner. So that's where our model helps, because what I'm plotting here is not my estimate of the prevalence. What I'm plotting here is the probability that prevalence exceeds the 20% policy threshold. Now, in the trade, this map is known as the pink map, and that's actually the problem with it, because pink means it's a 50-50 call. So if I focus in on particular areas of this map, here, both the survey data, which are essentially all blue, and the environment, which informs the colour mapping behind it, are telling me this is a low risk area. There's a low probability here of exceeding the 20% threshold. So we're very happy there. Notice that even when there isn't any survey data, the environmental relationship with temperature and vegetation greenness is enough to make me confident that these areas are below the 20% threshold. There are others where I'm doubtful. Here, I'm at the opposite end of the spectrum. I've got survey data, the dots are black, the environmental model is consistent with that, and we're pretty sure that's a dangerous area. And then finally, we've got a transition zone, where you can see the blacks and the blues are intermingled, And the environmental model allows some gradations to be pretty sharp. We're going pretty quickly there from yellow to red. Others, where it's pink, we're not sure. So that's helpful. But firstly, it's only in Cameroon. Secondly, there's all these pink areas. What are we going to do about them? Well, the statistician's answer is get more data. And the scientist's answer to that is don't be so naive. Right? If you want me to get more data, you've got to recognize that we're dealing with expensive technology in a poor country, a poor set of countries. We cannot afford to go and do more parasitological sampling, blood sampling. Furthermore, we really rather not, because it's not a very safe thing to do in these environments. You don't really want to go around pricking people's arms in environments like this. So we're not going to do any more blood sampling. But at this point, some very ingenious people at WHO Geneva come up with the idea that when you go to these villages, instead of taking blood, you will simply take a photograph. And this is a photograph of a mature lower worm infecting somebody's eye. And you ask this lady 3 questions. Have you ever suffered from eyeworm? If yes, did it look like this photograph? If yes, did it go away within a week? Remember I told you it wasn't a particularly serious condition. 3 yeses and we'll call that a plus. Everything else we'll call a minus, a negative result. Now that sounds pretty crude compared to looking down the microscope and seeing little beasties in the blood, but by doing some surveys in villages where you both ask the questions and take the blood, you can show, again using simple statistical models, that actually the relationship is remarkably good. These surveys, as you can see, were done in very different parts of Africa. Congo, Cameroon, DRC, which is the huge, great big country in the middle, west and east, separated by many hundreds of kilometres, and you can see qualitatively a very similar relationship, which actually looks more impressive if you merge it, and you can see that actually those surveys give an almost identical calibration relationship where it matters. Because although there are no numbers on these axes, I can tell you that the policy relevant threshold is kind of down here. And it turns out that 20% parasitology is sort of equivalent to 40% RAP-lower, questionnaire-based. So the idea now is that we have some evidence to say that instead of getting accurate information on parasitological prevalence, which is expensive and dangerous, we can get accurate information on RAP-lower prevalence, which is safe and cheap, and refine our maps. And that's important because we've got 19 countries to visit. So using that idea, we turn the data set into something much more impressive. There are between 4,000 and 5,000 points on this map, and every one of those villages has been surveyed by field epidemiologists, asking the RAP-lower questions, reporting the results back, and we then overlay it on, obviously, a GIS system to get a map. And what does that tell us about prevalence? This is our best guess at how the prevalence varies across that rather large geographical region. But more particularly, in going back to the policy relevant information, here's the updated version of what was the pink map. Apologies for the inconsistency in the colour coding. Red is dangerous as before, safe is now colour-coded blue, and you can see that the corridor of uncertainty is much, much narrower, even allowing for the fact that the map is over a much larger scale. So there are still 1 or 2 residual areas here where the corridor of uncertainty in cream is really quite wide, but generally speaking we're now very confident of rolling out the prophylactic treatment in all of the blue areas. We know we're going to have to put in precautionary measures in the red areas, and we have a relatively small areas of doubt where it's an interesting question as to what you should do, which I'd be happy to talk about in questions if anybody wants to pick me up. But that's essentially the story so far, and so the take-home message is that if you're going to couch policy guidelines in terms of things being true or not, and you're dealing with uncertainty, then you have to conduct risk mapping, and you have to accept that there is a probabilistic element to your decision making, and the job of the statistician is to quantify and make a difference between things being almost certainly like so, probably like so, possibly like so, almost certainly not like so. What you do with that information is sometimes difficult, but that's the role of the statistician, to quantify the uncertainty in the decision making. And our involvement in this project, which is obviously a multinational project, led to those additional surveys in thousands of villages, led to the refinement of the map so that we do now have a useful risk map extending over all 19 APOC countries. The program is continuing, it has maybe another 10 years to run, and the map is being used to decide where we can safely distribute the prophylactic and where we need to be somewhat more cautious and proceed rather more slowly and gracefully with backup medical support. Thanks for your attention.